All right. What is calculus all about? Some of you have already seen, to get into this class, you need to take like, you either need to place into it, or maybe you've had already Calc AB or BC or something like that. So you've seen calculus. What's it about? Why is calculus such a powerful? Why do we require all these different majors to take this course? Yes, it's one of the pinnacle achievements of the human mind. That too, of course, that's what I like about it. But why is it so powerful? Tell me your name. Annabelle, Peter, Dan, Sid, Treya, Jenny, Steve, Annabelle. Beautiful, beautiful. The first thing the calculus helps you understand is change. Absolutely. Change. Calculus is a way of understanding change. What changes? Everything changes over time. So if you can understand how things change over time, you got a big leg up over somebody who can't, who doesn't understand change. What else does calculus help you understand? Peter. One more time. Problem solution. Yeah, it's definitely a way of thinking. It's a set of tools, technique for answering problems and giving solutions to problems. Sort of all of math is supposed to be developing that skill of analytical problem solving. Tell me your name. Fatima. Fatima. Go ahead. Systems, yeah, systems. What systems do over time is they accumulate. So let's call this accumulation. Okay, these are the two things that calculus is really the study of: change and accumulation over time, how a system has accumulated over time. And there's a fundamental technique that's used in calculus to give you techniques for saying something about change. And that is what I'll call infinity. Okay, so calculus is the first place where we really deal with infinity in a serious way. All right, so let's do an example. Let me show you something with change and accumulation, and then we'll talk about it. So here's an example. All right, it's the first week of class. You're in the dining hall. The food is, there's no limit on the food, right? You just swipe in and it's what. Okay, so the first day, let's call this Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And here's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this is like how many sandwiches you ate in the dining. Okay, sandwiches in dining. Sandwiches eaten. So on Monday, you're like, oh, cool, sandwiches. I'll have 2 of them. And on Tuesday, you're like, that was great. I'll have 3. And you're like, no, that 3 was a little much. Let me have just 1 on Wednesday. And then you're like, I weigh over 8 and you vomit. And on Thursday, you have -1 sandwich. And then on Friday, you're like, I don't want to eat today. I've had enough. And on Saturday, you have 1, and on Sunday, you have 1. I'm just making something up, right? Here's the kind of thing. Some piece of information, some data tracked over time. All right. What is the accumulated number of sandwiches? So sandwich accumulation. In other words, how many sandwiches on each of these days? Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. 1, 2, 3, 4, 5. 1, 2, 3, 5. Okay, so we started the week empty stomach. On Monday, we had 2 sandwiches. How many sandwiches have we accumulated by Tuesday? Sid. Well, we had 2 on Monday, and we had 3 more on Tuesday. 5, right? So that's 5 sandwiches that we've accumulated from the beginning of the week. Okay. By Wednesday, we've accumulated 6 sandwiches. By Thursday, we've accumulated 5. We lost 1. Right. So we're back to 5. On Friday, still 5. We didn't eat anything. Saturday, 6. Sunday, 7. Oh, so look at that. By studying accumulation, you could say on average, you get 1 sandwich a day. Right? That's the kind of thing you can study from the accumulation. The other thing we can look at is change. What was our change in how many sandwiches we ate on a given day? So here's Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Okay. On Monday we went 1, 2, 3, 5. Monday we went from 0 to 2 sandwiches. Tuesday, how many more sandwiches did we eat Tuesday than Monday? 1. How many more sandwiches did we eat Wednesday than Tuesday? We went from eating 3 sandwiches to eating 1 sandwich. -2, -2. Our change in the number of sandwiches eaten on Wednesday is -2. Okay, how about the Thursday? From Wednesday to Thursday. On Wednesday, we eat 1 sandwich. On Thursday, we eat -1 sandwich. -2. We went down by 2 again. So this is again -2. Okay, everybody see that? How about Friday? On Friday, we went from -1 to 0. So that's a 1. That's a gain of 1. From Friday to Saturday, gain of 1. Saturday to Sunday, 0, flat. All right. That's change. The change, what was that? How much did we change from day to day? As opposed to how much did we accumulate throughout the week? So this is how much we changed from day to day. This is how much we accumulated throughout the week. So far, so good. You could study how much, what was the change in how much we changed, or what was the accumulation of the accumulation. You can do these kinds of things. You can also say, okay, once we've looked at the change, let's look at the accumulation of the change. How much did our change accumulate over time? How much did change accumulate over time? Change accumulation. Let's look at this. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Saturday, Sunday, okay. 5, 5. On Monday, we accumulated. The change in accumulation, we went from 0. I'm just applying the accumulation operator. What we did to accumulation is we had like a running tally from here to here. But now let's do a running tally from here to here. Everybody see what I'm doing? Anybody confused? Here's a rule in this class. If you're confused, look around. There's 100 people here. If you're confused, 30 other people are confused. Do them a favor and raise your hand and ask something. Even if you don't really need it, I think I know what he's saying, but I don't really need that advice. Those other people do, okay? So let me ask again. Anybody confused about what we're doing? All right. Finish this graph on your own over the next minute. So I'm looking at the accumulation of the change. So if I started at 2, then there were two changes on Monday and 1 change on Tuesday. So I accumulated 3 for Tuesday. By Tuesday, my accumulation had changed to 3. The change in accumulation was up to 3. And then I lost 2 on Wednesday. So that means I'm back down to 1. Finish the rest of the graph. Give me a hand up when you're done. People still working? Anybody confused about what Thursday's entry will be? Anybody want to talk about what Thursday's entry is? You want to tell me what Thursday's entry is? Tell me again. 0. Okay, so Wednesday we had 1. maybe it's hard to see. This Wednesday's accumulation was -2. This Wednesday's accumulation was also -2. We went down by 2, we went down by 2. So we have -2 and -2. So this is at 1. So now I'm going to accumulate -2 for Thursday. So from 1, if I accumulate -2, I get -1. Beautiful. Okay, and then I accumulate 1 on Friday. From -1, I get to 0. I accumulate 1 more for Saturday. I get 1, and I accumulate nothing on Sunday. So I stay at 1. Beautiful. Okay, there's also our sandwich accumulation. We could look at the change in the sandwich accumulation. So what's the change in accumulation? Not the accumulation of the change, but the change in accumulation. Okay, you know what graph I'm going to make now? Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. All right, so we started with nothing. The change from nothing to 2 is 2. Now from 2 to 5, Thursday it was 5. What's the change? 3. That's 3. From 5 to 6, the change is 1. From 6 to 5, the change is -1. From 5 to 5, the change is 0. From 5 to 6, the change is 1. And from 6 to 7, the change is 1. Okay, so this is a very, very basic example of how you study change in accumulation. Anybody noticing? Tell me your name. Poland. H. Poland. 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 Sid. Dan. Treya. Peter. Steve. Janine. Tell me again. Janine, like Janine and Janine, and did I have somebody over here? No, I didn't learn anything with it. Tell me your name again. Annabelle. Yeah. Annabelle, Peter, and H. One more time. Poland. Poland. Tell me what you notice. This graph and this graph and this graph are all the same graph. If you take the change and then compute the accumulation, you get back to the original function. If you take the accumulation and then you take the change, you get back to the original function. This is what we end the semester with. These are the first and second fundamental theorems of calculus. Okay, so this is fundamental theorem of calculus 1, fundamental theorem of calculus 1. This is the fundamental theorem of calculus 2. Or maybe 1 and 2 are the other way. All right. Change and accumulation are inverse operations of one another. And this is a concept that you can understand. That you didn't learn this in first grade. You should have. Never mind about what we teach in schools. All right. This is a very basic concept, and it's a concept that is fundamental to the power of calculus. It turns out that change. So what is change? How does change manifest itself? How does change manifest itself geometrically? What are we looking at when we look at the change from 3 to 2, from 2 to 3, from 3 to -1, from 1 to -1, right? That's the change function we're looking at geometrically. Tell me your name. Hurry. We're looking at slopes. Change geometrically is slope. The geometry of change geometrically. It's slope. And what is accumulation geometrically? So we had 2, then we added on 3, then we added on 1, then we added on -1. Hurry. The area. Okay, accumulation geometrically is area. running areas. All right, so we need to understand, in order to understand things like change and accumulation of various systems, well, we don't have to think about it geometrically, but why wouldn't we think about it geometrically? Because we have, this whole part of the brain that's responsible for eyes. Our eyes are extremely powerful computational devices, and things that we can see with our eyes can illuminate. Even the word illuminate is relating to eyes, right? Lighting up. So it illuminates the basic ideas of what's underlying. So geometry is slope. Change is slope geometrically. Area geometrically is accumulation. When you think about it geometrically, is area. These are extremely simple concepts. Okay, we're going to put them on steroids and think about them in very fancy ways, but the concepts themselves are very, very elementary. Okay, has anyone seen the fundamental theorem of calculus before? Okay, a couple of people. So a lot of you have taken calculus, but maybe we don't do a great job of explaining just how simple these things are. Why is area the opposite of slope? This is why. Okay, we're going to prove these things for you. What's the fancy math word for slope? When you find the slope of a function, instantaneous slope, derivative. Okay, so that's the first half of the course. Is slope, is derivatives. Derivative, you should think of derivatives as being easy. It won't feel that way, maybe, depending on the particulars of the function we're looking at. But computing derivatives is easy. The fact that differentiation, the computing derivative, is the opposite of accumulating area, is fundamental to being able to compute areas. Computing areas is hard. What is it called when we compute the area? Sid? Integral. Okay, this is what's called an integral. In fancy language, this is what's called an integral. In fancy language, it's called a derivative. Derivatives are easy. Integrals are hard, in the sense that there's not usually a function that explains what the graph of the integral is. But this being, of course, the integrals that you'll see are the ones that you can write a formula for typically. And the reason you can write a formula for them is the fundamental theorem of calculus. Okay, the reason you can find a formula for them is because you can differentiate, you can figure out what a derivative would be of your given area function. I'll explain all of that. Then you can integrate. All right. That's all the calculus. You've now taken a course in calculus. Done. I'll see you in December. All right. There's one more idea, as I said. Question? All right, now. Ari, Peter, Sid, Dan, Treya, Jenny, Annabelle, Steve, Joe. Poland. Okay. Where were we? We've had, that's it. That's a course in calculus with one extra little thing. As I said, this is discrete calculus, which is very simple, obviously. Is anyone confused about what we've done so far? If I gave you some graphs like this, you'd be able to compute the change function and the accumulation function of these things. All right. The thing that makes calculus difficult is that these two very simple concepts are paired with another concept that, at least in theory, in principle, is simple, but you'll see just how subtle it is, which is the principle of infinity. The principle of infinity is also very simple. It's that if you have given a hard problem, so here's the principle. Given a hard problem, break it into infinitely many, infinitely small problems. Okay, break it into infinitely many, infinitely small problems. Solve each of the infinitely small problems and accumulate. Okay. Solve small problems. Solve small. Right? That's the principle of infinity, if you will. My friend Steve Strogat like to call it. So the principle of infinity is whatever problem you have, you're going to break it up into not just really like dicing. You're going to dice all the way down to microscopic level, all the way down to nanoparticles, down to infinity, which doesn't exist in the real world. Okay, and each of those little pieces, you're gonna solve whatever problem you're interested in on those tiny little pieces where the problem is very easy, and then you're gonna figure out a way to put it all back together. Right? Let's see that. So infinities is a really subtle concept. Okay, so let's talk about infinity first. Has anybody heard of Zeno's paradox? What's your name? Timothy? Tell me about Zeno's paradox.
Running like half the race, and then after that, you have to infinite, I guess, finite derivatives, and then their conclusion was that therefore it would take infinite amount of time, but shouldn't have.
Absolutely. Okay, so let's say that again. Lost it. Timothy. Okay, so this is Timothy's version of Zeno's paradox. Timothy is exactly right. It's exactly what Zeno said. So Zeno's like 450 BC. Okay, one of these ancient Greek guys. Zeno says motion is impossible. There's no such thing as motion. No such thing as motion. You cannot get from point A to point B. If you want to go from point A to point B, such as in a race or any other context, you first have to go halfway. If you manage to get halfway, you then have to go halfway to the halfway, quarter of the way. Okay, but in order to get, even if you manage to somehow get a quarter of the way, then you have to go halfway there. That's an eighth of the way. And then you have to travel a 16th of the way. Then you have to travel 1/32 of the way. You have infinitely many things that you have to do in order to get from A to B. Therefore, motion is impossible. Why is it a paradox? Motion is obviously possible. I can go from here to here and that and I got it. What's wrong with what Zeno is saying? Why is this paradox? How do we resolve this paradox? Tell me. Douglas? Yeah, well, that's what makes it a paradox. Obviously, he's wrong. But where is he wrong? Douglas, Timothy, Ari, Peter, Annabelle, Jenny, Colin, Sid, Dan, Steve, Joel.
Yeah, still approaching.
That's right. He's struggling with the principle of infinity. You have infinitely many steps. How can infinitely many steps possibly accumulate to a finite number? Here's half. Very simple. Half is quarter plus an eighth plus 15 out to infinity. Out to infinity. Any finite amount of that will not give you to B. You can't get to B with a finite number of steps. But with equally many steps of that kind, you go from A to B. Okay. You also had another one where you can't even start to move. Because in order to get from A to halfway to A, you first have to get from A to a quarter of the way to A, and you first have to get from A to an eighth of the way to A, an eighth of the way towards B. Right? So you can't even start. Not only can you not get from A to B, you can't leave A. It's just nonsense, and it's because he did not understand infinity. He wasn't comfortable with infinity. Nobody was really. Archimedes could play with infinity. He gets maybe the first crack at calculus. But he didn't have all the tools and techniques that Newton and Leibniz, an Indian named Madhava, a couple of hundred years before Newton and Leibniz, people have figured this stuff out. Like, if you think about it this way, in the year 1670, there were like 3 people on the entire planet that understood calculus, that understood something about calculus. And now there's room for 100 kids, and there's thousands of rooms like it all around the country. Right? We boiled this down to something very simple. That's what science is supposed to do. So these concepts are simple, but you should not just, you should appreciate how difficult they are before they've been boiled down. To the point where somebody really famous who's done a lot of thinking really stumped people for a couple millennia about this concept of infinity. So infinity takes getting used to. What you are or aren't allowed to do with infinity, how it works, these are some subtle things. All right. So that is really underlying some very simple ideas of practical change and accumulation, is this tool of infinity, limits, continuity, derivatives, which are instantaneous rates of change, areas which are accumulations of infinitely small pieces and infinitely many of them. And how do we do all of this? That's what that's the real thing about it. Right? That's what we're doing. All right. Now, there's really one more thing that I have to tell you today, which is, okay, so we're talking about accumulation of skill. That's what this course is going to be about. As we said, you need to practice them. It's not enough to meet in person here and have a conversation with me. You have to go home and think about these things, read, watch other YouTube videos, whatever it is that's going to solidify your understanding. Here's something that, in my experience, makes it very difficult to do calculus. If you do not have fundamentals in pre-calculus concepts, someone who learned fractions not that great, and then got to be in fractions in 5th grade or something. Then you get to algebra. You can do most of algebra, except when algebra gets some fractions in it, things get messy and muddy. And then you get to trigonometry, and you can do most of trigonometry until it gets to all of trigonometry is fractions. But you can do, like, there are parts that if you have a hole in your understanding of like some little concept, you will make it extraordinarily difficult to succeed in calculus. Okay, so what we're going to do these first 2 weeks is try to make sure there aren't any holes. So let's build up, and if there are, that doesn't mean you need to drop calculus. It means you need to put in a little bit of extra time to fill in those. They're not hard to fill in, given the fact that you've placed into this course already. Okay, you can all do it. It doesn't mean you need to drop the, but it means you have to do it. Because if you don't, mid-November is too late to realize like you need a refresher on fractions. Now you need a refresher on the quadratic formula, or you need a refresher on sines and cosines, whatever else is going to be occurring throughout the course. Okay.